Okay. So at least the mirror is related to algebraic geometries. But so I would like to present some joint works with two postdocs, Yusi Kim and actually this, sorry, the Yunyoung Cho and Yusi Kim. So this is, well, actually by now, we understood the mirror symmetry of Turing manifolds by the works of our collaborators, Fukaya and Ohta and Ono, and in the previously Cho and myself. So we are trying to extend this kind of mirror symmetries to non-toric, at least Fano manifolds. So the first test case is this so-called Gelfand Cetlin integrable systems. So let me start with what this system is about. So you can, okay, you start with some partial flag manifolds. The partial flag manifold actually appeared in this area in Gromov-Witten theories in the beginning of this development that has been studied by Gelfand and Bum-Sik Kim and other people. And at that time, they already noticed some relation of this Gromov-Witten invariant and some Landau-Ginzburg theories through by some kind of stationary phase integrals. And there is also an attempt to construct, we are trying to construct the mirror of these or Landau-Ginzburg potential functions out of this open string version, the so-called flow homology theories. And this is the part of our attempt in doing that. And also, there is some work by the Ueda and Nohara, which studies some non-displaceability of Lagrangian fibers of this particular manifold through some the study of some potential functions that Fukaya and myself and Ohta and Ono constructed. So we are going to apply the similar theories to this integrable system. So let me now start. So the partial flag manifold is a complex manifold parameterized by a nested sequence of complex vector spaces in Cn, as you might all know. So I'm just give the definition. And the example is like F13 is CP2, and F24 is Grassmannian of two planes in four spaces. And if this nested sequence is complete, and it's called complete flag manifolds. And there is a natural symplectic form on this space through the so-called construction of coordinate orbit. So you look at this natural action on the dual of Lie algebras, and that you look at the orbit, and there is a natural symplectic form on this coordinate orbit, so-called the Kirillov constant Suryo symplectic form. And actually, we have explicit description of this symplectic form in this way. And we are basically trying to study some symplectic topology of this particular symplectic manifold. Oops. Yeah. And this space has a natural so-called completely integrable system. So in general, the completely integrable system is the existence of some n real-valued smooth functions which are so-called in involution. In other words, the Poisson bracket between each pair of that set becomes 0. And in general, this n collections of smooth functions may not be independent. So there are some locus where their differential do not span the whole cotangent space. So, but out of those singular locus, that n functions defines natural projection from this simplex manifold X to the n-dimensional real space. So this kind of system is called completely integrable system. And one big difference, one important difference between the general completely integrable system and the toric manifold is that these projections as a map from the whole space to Rn may not be smooth everywhere. So it is smooth on open dense set, but it may not be smooth on those lower dimensional locus. But one good thing about this Gelfand-Cetlin system is that this map is at least continuous through the singular locus. So one of the important things we have to understand in relation to this study of these fibers is to describe the geometry of fibers. Okay. And the way how this projection becomes completely integrable system is through by this construction of Guillemin and Sternberg. What you do is you consider this n by n matrix, a complex Hermitian matrix, and you look at these eigenvalues. If you look at the full matrix, you will have n eigenvalues, they are real eigenvalues. And then you look at the nested sequence of this square matrix by removing one column and one row, and then you look at this eigenvalues of this submatrix, and we denote this set of eigenvalues by lambda j k. So in this way, you will be given n times, well, how many? N times n plus 1 over 2 eigenvalues. So you consider this as a map to the R to the n times n plus 1 over 2. So that's that projection map I described for the general complete integral system. So in that regard, and actually one non-trivial fact is that considering this eigenvalue as a function on this cosine orbit or partial flag manifolds, and actually their Poisson bracket with respect to this Kirillov KSS form actually becomes 0. So that's the theorem by Guillemin and Sternberg proved a long time ago. And so this is some examples, simple examples. Look at Hermitian matrix in this cosine orbit, which is, let's say, diffeomorphic to this full flag manifold F3. And you compute these eigenvalues. And this, you compute the eigenvalue of submatrix, and this is the one. That provides some position of that element in that space. Okay, so now I want to, we know that when you're given Turing manifold, the image of this projection is some convex polytope. And this Gelfand Cetlin system also has similar structures. But the structure of polytope is a little more complicated than this toric case. For example, if you look at this particular polytope, in general, this polytope is called the Gelfand Cetlin polytope. And the corresponding polytope of F3 looks like that picture. And if you look at the vertices, one of the vertices in the right front, there are 4 edges coming out of it. So this is so that means that means this part is not smooth. Is not, what do you call this? In the toric case, the smooth Turing manifold has exactly the n number of linearly independent vector coming out of it. In this particular vertex, there are 4. So then corresponds to that this, anyway. So this is not the kind of polytope you see for the Turing manifold. Okay, so in general, this polytope, structure of this polytope can be described by some combinatorial diagram, which we call ladder diagram. And it turns out, so let me explain what this ladder diagram is. So we list the set of those eigenvalues of the matrix and the submatrices in this way. So in the main diagonal, this is the list of the eigenvalues of full matrix. And then the off diagonal, this list is the eigenvalues of the first submatrices and the second submatrix and the last one. So the last lambda 1,1 is nothing but just the value of the 1,1 entry of the matrix. Okay? And this is we called ladder diagram. So we just put the name for the later purpose. So I'm going to call the bottom, this vertex, the origin, the red vertex. And then you look at this top vertex, the blue vertices, the top vertex. Okay. And we call the path from the red dot to the blue dot, the minimum, the shortest path from the red dot to blue dot, the positive path. Okay. So any such positive path always goes to the right hand and vertical. And this is the actually theorem proved by An and Cho, and not that Kim, another Jang-Soo Kim, I think. And they actually proved that the positive path in the ladder diagram, one term corresponds to the faces of this Gelfand Cetlin polytope. So there is you look at this ladder diagram, and each positive path in the ladder diagram corresponds to one face of this Gelfand Cetlin polytope. So this is a very important result for our further study. So let's look at these examples. So the face. Actually, I didn't explain. So each face of this Gelfand Cetlin polytope corresponds to the union of positive paths. So let me Oops. Oops. Oh no, where is it? Oh yeah. Okay. So let's look at this. Which diagram, sub-diagram corresponds to this faces of Gelfand Cetlin polytope? Okay. The first one, you see that this is the union of two positive paths. So this corresponds to some face of this Gelfand Cetlin polytope. The second one also consists of union of positive paths. That's also corresponds to some face of polytope. But this one does not cover the blue dot. So each face corresponds to the union of positive paths covering all the positive top vertices. So the third one does not cover this one top vertex. So that does not correspond to any face of polytope. On the other hand, this fourth one, let's say this one is union. Okay, this one, includes some non-positive paths starting from here, red dot, to the, let's say, the over there. So there is some places which doesn't come from positive paths. So this kind of sub-diagram cannot correspond to these faces of polytope. Okay, and then there is some relation. In toric geometries, there is a description of this, the divisors, the toric divisors. Each structure of strata of toric divisors can be described by some positive order, partial order between some diagram. So this description of this, the faces and the structure of the gluing is similar to toric case. So we say the diagram, face, the gamma one is what do you call this? I will call just face. The union of these positive passes, I will also the face. So gamma 1 is included in gamma 2 if and only if this corresponding face is a face. So it's similar to the toric case. And then we can also compute the dimension of this face by counting the number of simply connected regions in the diagram. So in other H1, so just the H1 of this diagram is exactly the dimension of this Gelfand Cetlin polytopes. So for example, in this F3 case, I sort of described what this face diagram corresponds to the face of polytopes. So you see this green face is this diagram, which has two loops. So that tells you that the corresponding diagram should be two-dimensional as it shows. And then the size of these triangles is one-dimensional, and those diagram corresponds to those as drawn there. So each of them has this pi 1 is 1, and this one is 1. And this particular vertex that should be zero-dimensional, that corresponds to that face diagram. Okay, so this is some summary between the difference of Gelfand Cetlin polytope and toric momentum polytope. So interior, it turns out, this is a general fact, for any complete integrable system, the preimage of the regular values is always a torus. This is some theorem by general theorems. So that's the the first line just states that general fact. So Gelfand Cetlin polytope, as I say, it's a completely integrable system. And the interior, over the interior of this polytope, this is smooth. So the preimage should be Lagrangian torus. In the toric case, the preimage of the point on the boundary of this toric polytope is always lower dimension. It's still a subtorus, but it's not maximal dimension. Okay? But in this Gelfand Cetlin case, some fiber on the boundary of this polytope can be n-dimensional, maximal dimension. But those fibers are still isotropic submanifold. And one important factor about Gelfand Cetlin polytope is all the fibers turn out to be smooth isotropic submanifold. And I mentioned that the full projection may not be smooth across the boundaries, but even on the boundary points, the fiber turns out to be smooth isotropic submanifold. And some of the fiber may not be a torus. And some of the fiber could be non-torus Lagrangian submanifold. And in the point of mirror symmetry, actually those non-toric Lagrangian submanifolds play some role in the generating the Fukaya category of this partial flag manifolds. So in the toric case, all the generators of the Fukaya category of this toric manifold come from some fibers, the torus from the interior polytope. But in the Gelfand Cetlin case, those the torus, interior tori may not be enough to generate the Fukaya categories. So that's one important difference. And then we also have completed descriptions of which faces of this Gelfand Cetlin polytope corresponds to Lagrangians. I mentioned that each fiber is isotropic submanifold, but some of the fiber on the boundary faces could have maximal isotropic submanifold, in other Lagrangian submanifolds. And the question is, which face corresponds to such a Lagrangian submanifold, the Lagrangian face? So it turns out if this kind of property depends only on the face, not on individual points on the face. In other words, if some fiber over one point in the face turn out to be Lagrangian, and all the fibers in the particular face become Lagrangian. So we want to describe which faces corresponds to Lagrangian fibers. It turns out that there is a very nice description of it. So here is so I want to explain what the criterion for this fiber to become Lagrangian. So let's look at the block, this kind of Tetris game. So we are trying to play some Tetris game with this ladder diagram with this kind of L blocks. So in the Tetris game you place various kind of blocks, but in this game we are going to use only L blocks as you shown it. So we are trying to cover this the phase diagram by those L blocks as described here. a ladder diagram is said to be L-block fillable if those L blocks cover the ladder diagram obeying the following properties. The first one is the interior of two L blocks cannot intersect. Okay? And then there is no overlap when you fill it. The interior of L blocks does not contain any piece of any positive path. I said that each phase corresponds to the union of a positive path. So we are going to put this L block so that its interior does not include any piece of positive path. And the third one said you look at these blue edges in this L block. That's the top edges of this L, and the right farthest edges of this L block. And those two edges should be included in the positive path. Okay? So those three are the requirements in this Tetris game. And it turns out this phase diagram, the ladder diagram, is L block fillable if and only if the corresponding phase is Lagrangian. So if you play this Tetris game and you see this ladder diagram is L block fillable, and the corresponding phase must be Lagrangian. So let's look at some examples. So here, let's look at this partial flag manifold F7 with the main eigenvalues 6, 4, 2, and so on. So let's look at these two particular diagrams and see if they correspond to Lagrangian. Okay? And it turns out the first phase, you see the first phase is 7-dimensional because there are 7 loops. The second diagram, second phase is 11-dimensional because there are 11 loops. You can count it. And let's see, let's try to play the game. Okay? So let's try, you see the first one, on the left one, you can put the biggest, there is no place we can put this pink L block in this diagram, but you can put this blue L block in this diagram in this way. So, okay. Then let's keep doing it for the first one. And we can put this green L block into that. Oops. What do I have to do? Okay. So you can fit those 3 green L block in that way. And let's keep doing it. And then this L block consisting of just one square, you put 2. And you see the left one is completely filled that way. So this phase diagram corresponds to Lagrangian phase. On the other hand, the right-hand diagram, if you do that, there is the missing these squares. So this diagram does not correspond to Lagrangians. Okay, so and then what do we do with this understanding? So we want to, in symplectic topology, one of the important questions is which Lagrangians of manifold can be displaced by the Hamiltonian isotopic. So now we want to study which Lagrangian fiber in this Gelfand-Cetlin system is displaceable under the Hamiltonian isotopic. Okay? So for example, I just want to give you some intuitions about this displaceability by looking at these spheres. If you look at the sphere, 2-dimensional spheres, the equator you can see by try to move this by area preserving deformations. In this two-dimensional case, area preserving deformation is the same as Hamiltonian deformations. And you can easily see that the equator cannot be displaced from itself by area preserving deformation because each side, area of each side should be preserved. So you can, on the other hand, if you look at these small circles, that's also another Lagrangian fiber in this case by looking at these height functions. That small circle can be easily displaced by rotation. So that's displaceable. And in the toric case, this kind of studies is a little bit harder. In the two-dimensional case, everything is about area preserving geometries. But even in CP2, it's very non-trivial to see which Lagrangian fiber is displaceable. Okay? So that's what we are trying to study. And the motivation for such a study comes, of course, from this. It also plays an important role in homological mirror symmetries. And yeah, let me keep. So this kind of question is we are trying to study. So which Lagrangian Gelfand Cetlin fiber is non-displaceable? And one very general theorems for the complete integral system without using Floer theories is discovered by Enthoff and Polterovich. They, using their method, one can prove that there is at least one non-displaceable fiber in this Gelfand-Cetlin system. But we don't know where it is located. It could be on the boundary, or it could be in the interior, or we don't know what kind of geometry of that particular non-displaceable fiber looks like. And then Nishino, Nohara, and Ueda actually applied some the theory of this Lagrangian Floer theories developed by the Fukaya, myself, and Ohta and Ono, and applied this kind of theory to this particular this Gelfand-Cetlin fiber. And they studied some potential function, which I will explain later, and computed the critical points, and which point and studied which fiber corresponds to the critical point of these potential functions. And they proved there is at least one critical point for that particular potential function, which means there is at least one non-displaced Lagrangian torus over the interior point. And then Nohara and Ueda proved in some cases there is some non-torus fiber which come from the fiber over the point in the boundaries of this polytope, which is not torus, okay? But it's not displaceable. What they do is they actually explicitly computed so-called Floer homology for that particular fiber by describing all the holomorphic disks associated with it. So there is some actually non-torus fiber actually is non-displaceable. And it turns out that particular fiber should be included in the description of these generators of the Fukaya category of corresponding GR24 Grassmannians. Oops. Okay, so let's now look at this complete flag manifold F3. This is contains very interesting geometries. Okay? So you look at this is the polytope, associated polytope, and it turns out that red vertex actually the corresponding fiber is diffeomorphic to S3. So you can, and then you look at the fiber over the point on these red edges. They are the family of this torus. You can imagine that this torus degenerates to the sphere as you approach to this vertex. And the interesting fact about this full flag manifold is that you can actually prove that all the fibers away from these red edges are actually displaceable. This is proved by Paviniak. She actually proved all other fibers except those on these red edges are displaceable by explicitly finding the corresponding Hamiltonian isotopy. But it was open whether the fiber over these red edges are displaceable or not. Okay? And furthermore, actually, Ueda and Nohara actually computed the flow homology of the fiber at the vertex becomes 0. So that means we cannot tell whether that S3 fiber is displaceable or not. When the flow homology is 0, we cannot get any conclusion about this displaceability. If the flow homology is non-trivial, by construction that means it's non-displaceable. But when it becomes 0, we cannot tell any conclusion. So one of the main theorems we are able to prove is that actually we can prove that particular S3 is non-displaceable. But this is true by proving that all the Lagrangian torus fiber over the point in these red edges turn out to be non-displaceable. So and then by continuities, this Lagrangian S3 fiber is also non-displaceable. Okay? And so the question is, how do we prove that Lagrangian torus over the point in these red edges are non-displaceable? But the only way of proving such non-displaceability is to compute some kind of flow homology is not vanishing. Okay? And in general, well, so let me describe what this flow homology is about briefly. Okay, so that's the main tool for checking non-displaceability. So let's, oh, okay, this is before, maybe let me skip this. Quickly. I mean, these two screens actually states the generalization of that statement on partial flag manifold F3. That statement can be generalized for any full flag manifold Fn. So this is just, let me skip it. Okay, so now I want to go into a little bit of flow theories, because this is the main tool for study this kind of non-displaceability question. So we are working into the compact manifold, and the flow homologies we are going to use this Novikov ring as a coefficient ring. So the reason why we needed this Novikov ring is because there are a lot of holomorphic disks associated to this Lagrangian submanifolds. And this formal parameter T basically encodes the area of this holomorphic disk. So you look at this, So we needed to encode the homotopy class of this holomorphic disk. And this formal parameter basically the encoding just your homotopy classes. Okay? And then the general Floer theories is about the study, the intersection theory of a pair of Lagrangian submanifolds. For this particular question about non-displaceability, you're going to look at this Lagrangian submanifold together with its Hamiltonian deformation. Let's say this Hamiltonian deformation intersects transversely of this Lagrangian submanifold A. Okay? And then we are trying to form some kind of complex out of this intersection. You look at, since we look at this compact Lagrangian submanifolds, the number of and we are assuming the intersection is transverse, so there are only a finite number of intersections. So you regard those intersections as the generator of some module over these Novikov rings. Okay? And then you form some complex by defining this boundary map. And the boundary map is basically counting the number of these holomorphic strips, the cornered strips. So let's say you look at Q and P, and there is so-called Maslov index that associated to this holomorphic two-gon beta. And when that Maslov index, you look at the modular space of this holomorphic strips connecting these two pair of intersection points. And the dimension can be computed, so-called the Maslov index. And when the Maslov, there is also this translational symmetry on these Cauchy-Riemann equations. So when the Maslov index is 1, the associated modular space will have dimension 0. So you can count the number of such holomorphic strips. Okay? And that counting, the number is going to be the matrix element of some linear map denoted by delta. So the matrix element between Q and P will be the number of such a holomorphic disk. But the Maslov index is not the complete invariant of this homotopy class. So you can imagine that this homotopy class of beta may vary. Okay? By, for example, you can also attaching some interior sphere in the interior point, or you can also attach some boundary disk along the boundary point. This kind of operation changes the homotopy class of this beta. And by doing so, you can increase the area of such holomorphic strips. So you actually sum them over by using these Novikov rings. And that will define this boundary map delta on these free modules. Okay? And we want to have this boundary property delta square equals 0. The problem is, in general, delta square may not be 0. This is give rise to the so-called deformation theory of this boundary map. And okay. So if the delta satisfies this boundary property, then you can take this homology of it. This is so-called flow homology. Okay? But I want to emphasize that these flow homologies may not be defined in general. Okay? So you have to deform this boundary map. And that's what the Fukaya and myself and Ota and Ono developed in these flow theories. So here we call when the flow, the bound delta may not satisfy delta square 0, we say the boundary, the Lagrangian submanifold is obstructed. But in that case, you have to deform this boundary map. There are two ways of deforming the boundaries. So one is physics called boundary deformations, and another deformation is called bulk deformations. So roughly what bulk deformation is, the deforming the boundary map by inserting some ambient cycles. You look at the ambient cycle on this symplectic manifold. You look at the holomorphic this strip that intersect with these cycles at the interior points. Of course, this constraint will increase, decrease the dimension. So what basically this bulk deformation means, you are going to count the modular space holomorphic strips whose dimension is not just 0, but it's a higher dimension. Okay? And the similar construction can be applied to the boundary deformations. Okay? And if you do that, there are some Lagrangian submanifolds may have that kind of allowed that kind of deformations. We call such a Lagrangian submanifold weakly unobstructed. And so if you do that, deformations, and then you can define this so-called deformed flow cohomology. And the fact is that this deformed flow cohomology itself is invariant under the Hamiltonian isotopy. So if you can find such bulk boundary deformations for this flow boundary map, then you can define this symplectic invariant, and we call it deformed flow cohomologies. It turns out this question about finding bulk boundary deformations can be described some kind of Maurer-Kaudan equations, which leads to the notion of these so-called potential functions. And what is potential function is some natural function you can derive out of this deformation theory by studying some infinite Maurer-Kaudan equation. And for example, let's look at, in the toric case, this function can be easily described by looking at this momentum polytope. At least the final case, the potential function can be directly read off from the momentum polytope. And if you do that, for example, in CP2, for the Lagrangian fiber of CP2 case, the potential function is given by this one. Each term corresponds to the holomorphic disk associated that intersect with the toric divisors. One. There is exactly one for each. And this is the theorem starting from the Cho. Cho is the first proof, studied these potential functions for the CP2 case. And he proved the barycenter of this polytope for CP2 is the only Lagrangian fibers whose flow cohomology is non-vanishing. Okay. Yeah. So, okay. So in CP2 case, the only critical point, the only positions which admits some critical point of this potential function is exactly the barycenter of this the momentum triangle of CP2. Okay. And it turns out that's the only toric fiber that is non-displaceable. And the general study can be applied to arbitrary Turing manifold. That's what we did. And then let's go back to the Gelfand-Cetlin system here. So in this case, in fact, you look at, we can read off this potential function again in a similar way. In this, although the Gelfand-Cetlin system is not toric, it admits some kind of toric degenerations, such so that this Gelfand-Cetlin polytope itself becomes some toric momentum polytope. And using that observation, actually the associated potential function for this Gelfand-Cetlin system can be also read off by studying this polytope. And then Nishino, Noera, and Rueda studied the critical points of these potential functions. And they proved there is at least one critical point of this potential function, which turns out to be the beta center, some kind of beta center of this polytope, which is the end of, where is that? Oh, yeah. So the one interior endpoint of this red edges, that's the point which admits the critical point of that particular function. Yeah.
This is the potential that you are writing?
Yeah, this is the potential function corresponding to this polytope.
This gets exceptional collections such as alternate double points.
Exceptional collection, what do you mean by exceptional collection?
The mirror sound possible.
Yeah, probably there is also the mirror description of this by Rich, and I don't know. Yeah, that may correspond to, yeah, there is some description of this mirror, actually, yeah. Okay, however, the point, the other point on these red edges is another critical point. But we can actually deform this system by some bulk deformations. So the bulk deformation we are going, the cycle, ambient cycle we use is the Schubert cycles associated to some kind of the divisor associated to this phase. Okay, you look at the pre-images of this phase on this Gelfand-Cetlin system. We are going to use the two union of the Schubert cycles of this pink faces. And it turns out if you deform that flow boundary map using these cycles, the deformed potential functions turn out to have some critical points. In other words, the point on these red edges admits some bulk deformations, so that the deformed potential function admits this critical point. So this is the outline of the proof of non-displaceability. So we applied that deformed Lagrangian Floer theories I vaguely explained. And then the potential function, again, plays a crucial role. And this way, we deform the potential function by employing that Schubert cycle I just described. And then we apply the critical point theories. Okay? And so, and that's how we prove the non-displaceability of this fiber torus over the point in the red edges. And that's the end.
So in your red edges, can you classify how many these Lagrangian uprights of fiber.
They are all because any pair of fiber over the edges do not intersect. So that means they are all non-equivalent on the Hamiltonian isotopy. So there is a whole family of non-displaceable Lagrangian continuum of non-displaceable Lagrangian fiber. This is something.
So how is the fact that this one of these critical points in this barycenter determining the non-displaceability of the angle? How is this connected?
Question again? What?
So you were saying that there is some critical point in the barycenter.
Yes, yes.
So how is this connected with the angles?
Angle.
Yeah, I mean, displacement or non-displacement.
What do you mean by angle?
So if you were talking about this Lagrangian,
Yes.
so how the fact that the critical point is in this barycenter is connected with this displacement?
Oh, so by construction of this potential function, taking the derivative of this potential function actually corresponds to the applying delta to some identity element. So if the derivative becomes 0, that means the delta applied to this identity becomes 0. And out of this, you can actually prove the boundary map is identically 0. So that means the